Okay, hello and welcome to our first video lecture for Chem 101 in the spring semester. um, in this case, basically, my notes are written on paper, and this is the way we're going to be doing the videos, basically. The paper will take the place of the whiteboard, and I'll basically go through my notes, and along the way, I will explain various points, and sometimes I may go on to another sheet to work something out step by step for you. But essentially, this is what it is. And because I'm here to explain it and to state things in a way often that's a little bit different from the way the book is stated, then hopefully between me and the book, it'll help you sort of form an understanding of how things work. Starting at the beginning, which I guess is what we probably should do. Oh, and by the way, along the way, if there are any questions, I know you can't stop me in the midst of lecture. First of all, if there are any questions or anything you don't quite understand, because it's on video, you can always just stop it and back up a little and watch a segment again. Hopefully that'll help. But also, you could contact me via email if you don't have a very good description of the subject or what it is that you don't understand about it, then at least try to refer to what point in the video it was, in terms of time. Was it like 3.5 minutes in or something like that? Oh, and as I mentioned in class, the lecture videos I tend to do in smaller segments just because it takes forever to load a 75-minute video onto YouTube. So I tend to do them in 3 segments of about 25 minutes each. So there will be normally 3 segments for each lecture. Just be sure to watch them all and watch them in order. Okay, so again, starting at the beginning, chapter 1. I guess the first question to ask is, what is chemistry? Chemistry is actually going on all around us, even though in many cases we don't really recognize what's happening as chemistry. But at heart, a lot of things actually are chemistry. Anytime you drive your car, the burning of the fuel within the engine is a chemical reaction. And that's what propels the car. The car wouldn't be able to go without chemical reactions, not to mention all the chemical reactions that went into forming the plastics and the rubbers and things like that that are used in cars. So your own body runs on a series of chemical reactions where oxygen and food are transformed into energy and carbon dioxide and water vapor through chemical reactions. So yeah, and photosynthesis, where plants basically do the opposite of our metabolism, and the plants take sunshine and oxygen and water and turn them into glucose, which it then stitches together into chains of glucose known as cellulose, and that is the structural, basically what the structure of plants is fundamentally made of. That's chemical reaction. So the chemistry is really everywhere, even if you don't realize it. And as for what is chemistry, chemistry is usually defined as the study of matter and how it behaves and what it's like. So behavior and characteristics. So things like if you take this type of matter and put it together with that type of matter, does anything happen? And if so, what? So that would be like behavior. But also fundamentally, what is the matter like? Qualities as simple as what is its color? What does it smell like? What does it feel like? Is it hard? Is it soft? All of that comes under the heading of chemistry. Now, as for what is matter, matter can generally be thought of as simple as stuff, anything that physically exists. So basically nouns and pronouns, if you want to think of it that way, are matter, except for abstractions, like love or honor or dignity and things like that. Those are not matter. But people, places, things, animal, vegetable, mineral, those are all examples of matter. You, me, him, her, them, that's all examples of matter. So anything that exists physically, and by that what we mean is anything with mass and volume. And we'd better define those terms now. Mass is usually considered to be the measure of the amount of matter in an object. So that's kind of a circular definition here. Matter is something with mass. Mass means that it has matter, okay? But anyway, if it has mass, if it has matter in it, then that's matter. Now, here I want to make a distinction that we'll draw much more carefully and in more detail later, but I want to distinguish that mass is not the same thing as weight. They are related to each other, but they're not the same thing. So I'll just plant that seed there and we'll come back to it later. And actually, in one way in which mass is different from weight is that mass is not affected by gravity. Weight is. Mass is an inherent characteristic of an object. As long as you don't change the object, it will always have the same mass. And it doesn't even matter where you are, whether you're here on Earth or on the moon or on Mars or in outer space where there's no gravity at all, the object will have the same mass. Weight is affected by gravity, so weight will change if you're here on Earth versus on the moon or versus outer space where there's no gravity. It is possible for an object to have mass but no weight. Like, again, if you're in outer space where there's no gravity, your weight would be 0, but you would still have mass. On the other hand, it is not possible for an object to have weight but no mass, because in order for an object to even exist, it has to have some mass. Volume is just the space, three-dimensional space that an object or sample occupies. So if it has these two things, then it qualifies as matter. So now that we've defined chemistry, we'll look back a little bit at the history of chemistry. We're not going to go into detail on this subject right now because we're more concerned with learning sort of the fundamentals of, what chemistry is rather than what it was in the past. The history of chemistry is very interesting, but unfortunately, we just don't have time in one semester to go over it in any kind of detail. But anyway, chemistry, again, like I said at the beginning, chemistry is everywhere, even if you don't realize it. On the other hand, also, chemistry has been practiced by the human race for a very, 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 very long time, even though we didn't really realize it until relatively recently. As something as simple as harnessing fire and burning wood for heat, or using that fire to cook food, that's chemistry that's going on there. Even if you don't understand the fundamentals behind what's going on at the level of atoms and molecules, you're still doing chemistry. Our ancestors, almost as far back as harnessing fire, they were able to smelt metals. In other words, most metals like iron and copper don't occur as pure metals in nature. They tend to occur as part of what are known as ores, O-R-E-S. And those ores usually consist of the metal combined with something else, usually oxygen. So iron comes from iron ore, which is mostly iron oxide, in other words, rust. And that's why iron ore tends to look kind of reddish, because it's basically rust. And by basically heating it in the absence of oxygen, you can separate the metal from the oxygen, and you get your copper or your iron, which you can then use for tools or weapons. And then the oxygen just goes off into the air and joins the plenty of oxygen that's already there. That's a chemical process. That's a chemical reaction. Even though, again, our ancestors thousands of years ago didn't understand what was happening at the molecular or atomic level, they were doing chemistry. Also forming alloys. Well, alloys are actually just mixtures of metals, but the process of getting the metals that you can then form alloys with, that's chemistry. Tanning of hides. When you take an animal hide and treat it so that it will last for a long period of time and not rot, the changes you're making to that animal hide, whether you're doing it the way people back in the Stone Age did it, using all kinds of nasty stuff like brains and dung and urine to treat the hides, or whether you're using the kinds of chemicals they use today, it's still a chemical reaction. You're producing chemical reactions within that hide, that will make it less vulnerable to bacteria and things like that that would normally cause it to rot. One of the oldest, also one of the oldest reactions, it occurs a lot in nature, but also one of the oldest reactions harnessed by people was fermentation, where yeast can metabolize sugar and produce carbon dioxide and alcohol. That is a chemical process, and people have been doing it intentionally for many thousands of years. Making of soap, that's a chemical process also. And again, that goes back at least as far as ancient Rome, so at least a couple thousand years. And they were doing chemistry again, even if they didn't realize it. Where chemistry sort of first started to be treated as what we might at least loosely consider to be a science was in ancient Greece, probably about 2,500 years ago. In the ancient Greece, of course, they were very limited in the tools that were available to them for actually investigating scientific matters. But, as a result, what they mostly did was what they did about all kinds of philosophy. They thought about it, and they sort of deduced from logical processes what made sense to them and what didn't. And in fact, for many years, until fairly recently, science was considered to be a branch of philosophy because it was all part of a larger search for truth. Whether you're looking at moral philosophy, where you're trying to find out the truth of what is human nature, or what is good versus evil, or whether you're investigating more like physical or scientific philosophy, what is the nature of matter, that kind of thing. So it was all considered philosophy. So the first scientists, if you want to call them that, were actually philosophers, as we would call them today. And they generally philosophized about science as kind of a sideline to their main deal, which was, philosophizing about what we would now call philosophy, good versus evil and that kind of thing. The most fundamental question, concerning chemistry among the ancient philosophers, although they didn't call it chemistry yet, was the question of whether matter was exactly the same at the smallest levels as it is at the level that we can see and appreciate, or does matter consist of tiny little particles that are separate from each other and they just happen to be stuck together, and they're too small for us to see individually. So what we see might look like a sheet of paper, but in reality, that sheet of paper is made up of tiny little particles that are stuck together. And there were two sides to that argument. One said, basically what they were describing as those tiny little particles were what we now call atoms. And there were two sides to that argument. One side said atoms do not exist. Matter is exactly the same at the smallest levels as it is at the levels that we can see and appreciate. And the other side said, yes, atoms do exist. We just can't see them, so we can't really prove that they exist with the current technology in ancient Greece, but they do exist. And if we were able to see on a scale that small, we could actually see these separate little particles. Unfortunately for the history of science, the chief proponent of the argument that atoms do not exist was a guy called Aristotle, which I'm sure everybody has heard of. The chief proponent of the side that said atoms do exist, that is the guys who were right, was a guy called Democritus, who hardly anybody has ever heard of. And when you're in an argument about philosophy, basically nobody beats Aristotle. So for about 2,000 years, until about 1800, actually, the standard position within fields dealing with matter or chemistry was that atoms do not exist. And unfortunately, that had a very detrimental effect on the progress of science over the years. There's a lot that we probably could have done if people had been thinking in terms of individual atoms sooner. The alchemists which really sort of took off in ancient times, but really became a thing in the Middle Ages. The alchemists dealt with chemistry mostly in a trial and error method. And alchemy, of course, is where we get the word for chemistry. Alchemy itself comes from an Arab word, an Arabic word, which came to Europe during the Crusades, or as a result of the Crusades anyway. And from alchemy, we get chemistry. The alchemists were mostly concerned with basically trial and error kind of experiments. They did, though, along the way, discover a lot of useful information. They never did achieve their main goal, which was to find a way to convert common metals like iron or lead into gold. And I don't think they really understood the free market or market economics either, because if you were able to change iron into gold, then gold wouldn't be worth much because there'd be so much of it. But I guess you could cash in if you got in on it really early. Anyway, the alchemists didn't really take a very scientific approach by modern standards. Like I said, most of it was just trial and error. And they also mixed in a lot of astrology and magical thinking and things like that we wouldn't normally consider to be science today either. But they did sort of lay the foundation for what eventually became modern chemistry. We'll get into the history of the theory of the atom, whether it exists and what it looks like and what it acts like, in more detail in the future. So I'll sort of leave the history of chemistry there. Anyway, chemistry is often known as the central science. In fact, there is at least one textbook out there called Chemistry, the Central Science. And that's because you'll find chemistry sort of right in the middle of all of the other physical sciences. On one side, you've got biology, which involves a lot of chemistry. On the other side, you've got physics, which involves a lot of chemistry, particularly things like the structure of the atom and quantum mechanics. Those are fundamentally physics, but they have a big overlap with chemistry. And not only that, but biochemistry and medicine and pharmaceuticals, materials science, synthesis and manufacturing of things like polymers and other synthetic materials, environmental science, computers, particularly the manufacture of things like computer chips, how you manufacture the computer chips and what the chips are actually made of, because they're not just silicon, they're usually silicon mixed with other stuff. And that's where the chemistry comes in. And also geology. The rocks are made up of chemical substances, and you can actually study them. You can investigate the structure of the molecules that make up the rocks, and that's chemistry. Okay, there's a figure 1.3. It's not really important enough, so I'm not going to dig it out and show it. But figure 1.3, you can look at that, and it sort of shows the relationship between all the various sciences. And just as some examples of chemical processes, as I said at the very beginning, chemistry is always going on all around us. And so just quickly, combustion, anytime you burn something, whether it's gas in your stove or wood in a fireplace or gasoline in your car, those are all chemical processes. Rusting, corrosion, tarnishing, those are chemical processes. So if you're getting rust on your car, that's a chemical process. If your grandma's silver tarnishes and she assigns you the job of polishing it, tarnishing is a chemical process. And any kind of corrosion. So the terminals on the battery in your car get corroded from acid that leaks out of the battery over time. That's a chemical process. And in fact, the operation by which the battery produces electricity is itself chemistry. Your metabolism, as I mentioned before, cooking and baking, synthesis of polymers and other synthetic materials, including drugs, chemical processes, and the manufacture of many consumer products, things like soap and mouthwash and detergents and deodorants and things like that. That's all chemistry. Okay, so now that I've convinced you that chemistry is the most important of all sciences, let's sort of pull back a little bit and get a little bit more general and talk about the scientific method. As I mentioned, you can kind of think of the alchemists of the Middle Ages as being sort of the beginning of modern chemistry, but their approach was not exactly scientific by modern standards. So what is scientific by modern standards? Well, anything that follows the scientific method is scientific by modern standards. Yeah, the catch is that the scientific method isn't really very specifically defined. So the scientific method is kind of loosely defined, and it's a series of steps or procedures that you can use to sort of guide yourself through the discovery process in order to make sure that your eventual conclusions are as accurate and valid as possible. There are different ways to finding information and explanations, but you normally begin with making observations. And what's interesting as we go through the scientific method is to kind of think about how the scientific method is really kind of a formalized version of the process by which we learn things. Even as children, we're kind of using a sort of primitive version of the scientific method without even really realizing it. And for that matter, animals do it to some extent too. When you're trying to train your dog, or when a cat investigates something to see if it's good to eat, they're kind of using a very primitive version of the scientific method. So normally you begin with an observation of some natural phenomenon, something that happens, and you wonder why. Okay. And what you do is you think about it a little while and you come up with a hypothesis. That's just a tentative explanation for why something might be happening. It's based on the observation, and it should be your hypothesis should be consistent with all known information about whatever phenomenon you're observing, including any applicable scientific laws if you're aware of them. And what the hypothesis does is it sort of acts as a guide for further investigations, which you will accomplish via experiments. Experiment is sort of a controlled situation where you set things up to test your hypothesis. And you try to do an experiment in an environment that's as controlled as possible. And you basically conduct your experiment, you observe the results, and you see if they're consistent with your hypothesis. If they are consistent with your hypothesis, that's good, and your hypothesis will survive for the time being. But it's always a good idea to do these experiments more than once. So you'll probably do the experiments again. Maybe you do the experiment again, doing it exactly the same way, except you change one thing and see what the results are. And if the results are different, then that's probably because of that one thing that you changed. So you can sort of refine your hypothesis by saying, okay, this is the way things probably are. And if we change this factor, it has this effect. And then you could do the experiment again and change one other thing and say, okay, if we change that, then it has this effect. And all of this combines to sort of reinforce your hypothesis and to make it more accurate and more detailed. If the experiment does not back up your hypothesis, then you may have to reformulate it. And that's okay, because hypotheses in science are usually not totally correct the first time. Most of them end up being refined multiple times, or revised or refined multiple times before the final version actually emerges. It's also, at least in the world of formal science, it's also important to publicize your results. That's why we have so many scientific journals out there with so many papers being published all the time. It's largely because two minds are better than one. And thousands of minds are better than two. So you publish your results, you put it out there for criticism. Other people try to replicate your results, or they compare your results to what they got if they already did the experiment, and they critique your results. And collectively, you can come together and sort of find a common understanding of what's really going on. So sharing the results and sort of enduring the criticism of them is part of the deal in science. And that's the comparison of the results with others. It can confirm your hypothesis, or refute it, in which case you have to reformulate. Let's see, I was getting ahead of myself. So if the hypothesis ends up being sufficiently confirmed by multiple experiments, by multiple different people, preferably over a period of time, then it could become what's known as a scientific law. Or it could contribute to a scientific theory, become part of a theory. A law is a relatively simple summation of results of many experiments over a period of time. In the case of a law, it's usually pretty simple and straightforward. It's often expressed mathematically with an equation. And for a law to be considered a law, it must have no significant evidence against it. And one example would be, and it's also able to predict behavior in future situations. An example of that would be the law of gravity. Sorry, any objects that have mass will have a certain amount of attraction for each other based on the masses of the two objects and the distance between the two objects. And there is actually a mathematical equation that you can use to calculate the exact level of, or the exact magnitude of the attraction between two objects based on their masses and how far apart they are. That's physics, so we're not going to go into that much detail. But, sorry, you can also see from, if you use that equation, that in order for the magnitude of the attraction to be significant, one or both of those objects has to have a really, really, really big mass. So even though attraction does exist between any two objects that have any mass, it's not going to be significant unless one of those objects is really, really massive. So I put these two pencils down here. They both have mass, and they both have an attraction for each other based on the law of gravity. That, because the masses of the pencils are so small, though, that attraction ends up being so small that it's not even able to overcome the friction of sliding one pencil toward the other, and they stay where they are. On the other hand, if you were to take the attraction between this pencil and the Earth, the mass of the Earth is so huge that basically just about anything will tend to have a very significant attraction toward the Earth. And so the law of gravity predicts that if I let go of this pencil, it'll drop, and it'll drop towards the Earth, and it will keep going until it hits something that doesn't give way, like the surface of the Earth, or in this case, the paper. Now, I haven't actually dropped the pencil yet. As I said, one evidence of a valid law is that it's able to predict things that happen in the future. So I haven't dropped the pencil yet. The law of gravity, as I said, predicts that it's going to fall if I do let go of it. And so let's see what happens. If I let go of it, what do you know? It fell. So the law of gravity is supported by that observation. But the law of gravity, like I said, is very simple, very straightforward, and absolutely true. A theory tends to be broader than a law. It takes in a lot of different aspects of a concept, and maybe not all of the aspects of it are necessarily fully defined in detail. All of the elements of a theory, in order to be part of a theory, have to be well proven and testable, or falsifiable as the fancy term for testable, meaning that you can test it and you can confirm or refute it. Sorry, but some of the lesser defined aspects can over time be filled in, or may even be revised if they're found to be not, completely applicable. And an example of that would be the theory of evolution. The theory of evolution takes in a very broad array of factors and concepts in the development of life over a long period of time. So there's a lot to the theory of evolution. And the basic theory has stood the test of time, but various parts of it have had to be revised from time to time over the years. And there are certain parts of it where we don't fully understand what's going on or why things happen. Or in chemistry, atomic theory, the theory of the atom and the theory of its structure has developed over time. The theory that atoms exist and that they have certain properties, that is totally well established and nobody denies that anymore. But some of the details on the way the atom is structured or the way the subatomic particles behave, that is still under a certain amount of debate. And so that's what I mean by theory is well proven overall, but certain aspects of it may need to be filled in or revised over time. Okay. So I think that's a good place to end the first video since I've gone a little over 25 minutes. Sorry. And I'll pick up in part B in just a moment.